Hi guys, this is Math 1513, Northern Oklahoma College Algebra, Chapter 4, Section 3 in your book. We're going to talk about solving equations using solving logarithmic functions, using logarithms to solve equations. Okay, logarithms. Logarithms are nothing to be scared of. We call them logs. Logs are just something we use. It's a tool we use to solve equations with unknown exponents. For example, 3 to the x equals 9. Now it's obvious that x has to be a 2 because 3 squared equals 9. But, of course, we're going to have harder equations than that to solve, and this method of using logarithms will help us find out that x is going to be 2. I'll show you how to use logs to find that out. Let's take some easy exponential forms that we already know, such as I'm raising 4 to the power of 0, then 1, then 2, then 3, and I get 1, 4, 16, and 64. If I take these four exponential equations, I can rewrite them in log form. I'm not changing anything, I'm just rewriting them in a different format. Well, the first thing I'm going to do is write 4. And then I'm going to write the base down here. This is a base 4. You guys remember in an exponential equation, that big number is called the base, and the little number, the 0, is called the exponent. So we're going to put the base down here, and we say log base 4, and then I'm going to put the answer here, regular size. Log base 4 of 1 is 0, and the exponent's out here by itself. We say log base 4 of 1 is 0. We just put the base right beside the word log in the lower numbers. That's called a subscript. So log base 4 is written small, of the answer 1 gives us the exponent 0. And that's the whole idea. We want to get the exponent by itself. We're solving for an exponent. So we need to rewrite the exponential equation in logarithmic form so that our unknown, our x, is all by itself. Later on, these exponents are all going to be x's. Later on, instead of 4 to the 0 equals 1, it'll say something like 4 to the x equals 1. And we're going to have to rewrite it as log base 4 of 1 equals x. All right, so that's where we're headed. We're going to have an unknown exponent. We're going to rewrite it in logarithmic form just so that we can get the x isolated, get the x by itself, so that we can figure out what x is. All right, why don't you guys try and rewrite these last three exponential expressions and put them in logarithm form. So here we go. Log base 4 of 4 is 1. Log base 4 of 16 is 2. Log base 4 of 64 is 3. It's just another way of saying this exponential expression. You can write it in an exponential expression, or you can write it in logarithmic form. It's kind of like temperature. We can measure in Fahrenheit, or we can measure in Celsius. We're still talking about the same temperature. We're just writing it two different ways. So exponential and logarithm are two different ways of writing the same expression. And there's how we say all of them. Okay, we have two special kind of logarithms. They're called common logs and natural logs. I forgot my L. There we go. Whoops, that's horrible. Natural logs. All that means is they have a special base. Now see if you can figure out what the answer is here. Log base 10 of 100. That means 10 raised to what exponent gives me 100? Well, that's got to be 2, because 10 squared equals 100. All right? What about this? Log base 10 of, let's do 10,000. Equals what? So 10 raised to what exponent gives me 10,000? Well, that would be 4. Here's a couple others. Log base 10 of 100,000 and log base 10 of 1,000,000 equals 5 and 6 respectively. Okay, we call these common logs because they're base 10. And the thing that's cool about common logs is we don't need to write the little base 10. So if you don't see a base written there, it's understood that it's a common log of base 10. What's cool about common logs? We like common logs because we can plug them into our calculator. Why don't you guys grab your calculator and try that. Plug in log 100, find your log button, log 100 and hit equals, and you should get 2. Try those other logs on your calculator. See if you can get them to come out. Okay, natural logs are similar to common logs. They just have a base of e. Now what is e? I want you guys to find e on your calculator and just raise it to the first power so you can get a look at it. So it's going to be somewhere around your log button on your calculator. Find e and raise it to the first power. And you should get an irrational number that goes on forever, 2.7183, all right? It's a special logarithm, special base, 2.7183. We'll explain how it works later. But it's called a natural logarithm. And just like on the common logs, the base was 10, on natural logs, the base is e. So let's just do that exponential thing we calculated. We said e raised to the first power was 2.7183. All right? If I wrote it using log log, that's what it would look like. But what we do instead is we use the letters ln for natural log. I don't know why they didn't write nl, but they chose ln. Natural log. Since we know it's a natural log, we don't have to write the base of e. So I'm going to erase that. We know the base is e. Our answer is 2.7183, and our exponent will be 1. That's called a natural log. The base of e is understood. We don't have to write the e. We know that e raised to the first power gives us 2.7183. All right, pop quiz. See what numbers we would have to take the natural log of to get 2 or 3 or 4. See if you can figure that out. I got natural log 7.3891 equals 2. Natural log 20.0855 equals 3. And natural log 54.5982 will give us 4. What's cool about natural logs, again, we can plug them into the calculator. So find your natural log button, punch in these numbers, and see if you can get them to spit out 1, 2, 3, and 4. Okay, what if they ask you, just to mess with you, evaluate this logarithm without a calculator? Well, that's no fun. But since it has a base of 0.5, we can't use the calculator anyway. We have to use it, use our brain. So the first thing I usually do is I set it equal to x. And I go, okay, if I turn this into exponential form, it would be 0.5 raised to the x power gives me 16. Well, since 0.5 has an exponent on it, an exponent of x, maybe I should try writing 16 with exponents and see if I can kind of match them up. All right, we're getting there. I rewrote 16 as 2 to the 4th. Now they both have exponents, but their bases are different. So I got to figure out a way of making the 0.5 look like the 2 or the 2 like the 0.5. Now I know that 0.5 is 1/2, and 1/2 has a 2 in it, so I'm going to try that. And I'm getting closer. Now my 2, my 1/2, the 2 on the 1/2 is on the bottom. I would like that to be flipped over so it's a regular 2, just like my 2 to the 4th. How do I flip fractions over? I just make their exponent the opposite sign. So it'll look like that. Well, 2 over 1 is really just 2. So what I have is 2 to the negative x. So I have 2 to the negative x equals 2 to the 4. Now, since the bases are the same, since 2 is equal to 2, since 2 equals 2, since base equals base, then exponent must equal exponent. It just makes sense. And if negative x equals 4, well, I just divide them both by negative 1 to find out that x must be negative 4. And we could go all the way back to our original equation and plug it in with our calculator, 0.5 raised to the negative 4, and we should get 16. That's a good check. You don't have to check. I would. I advise that you check, but I'm not going to make you check. You just do that for your own good. How about this one? It looks scary, but it's not really. Now remember, a natural log has a understood base of e, and I'm going to set it equal to x. So now I'm thinking, okay, e raised to the x exponent is equal to my answer, e to the 5th. Okay, since e equals e, since our base equals the other base, our exponent must equal the other exponent. Just makes sense. And there we have our answer. X must be 5. Okay, what about this one? 2 log base 7 of 2,401. Well, that means 2 times the log. And remember, I like to set these equal to x because I'm looking for the exponent that I need. What is the exponent that I have to put on the 7 to get this to work out? Well, first thing I'm going to do is divide that 2 off of there. And I have this. Now I'm going to think, okay, 7 raised to this exponent equals my answer, 2,401. Well, I would like my bases to look the same, so can I write 2,401 as a power of 7? Well, that's 7 to the 4th. So now I have 7 to the x over 2 equals 7 to the 4th. Since 7 equals 7, that means x over 2 must equal 4. And I finish solving, and x must be 8. And finally, I'm going to show you how to graph using exponential form. So here's our log form. They want us to graph this. Well, we're going to change it back to exponential form just so we can get some x's and y's to graph. Now remember, back in junior high, f of x was called y. So now we have log base 6 of x equals y. If I change it back to exponential form, I have 6 raised to the y exponent gives me an answer of x. Now this is going to run a little backwards in your head, but we're actually going to plug in y's and see what the x's turn out to be. I'm going to put in different exponents for y, and we'll see what x turns out to be. So I'm just going to plug in some y's. Whoops. You always want some negative numbers and some positive numbers so you get a good picture. Let's see what happens. And it looks like we have these values. Now just transfer those values over to your graph, and you're good to go.